So let's continue with more examples involving the chain rule. In this next one, number 54, f is a function of the variable u. F of u equals 1 minus 1 divided by u. And u is a function of the variable x, which is g of x, and that is equal to 1 divided by x minus 1. We have to evaluate the derivative of f composition g at the point minus 1. So we have to, of course, first of all calculate the derivative in general, and then only we can evaluate it at x equal to minus 1. So that's what we do. So that means in the beginning itself we are applying the chain rule. So obviously this derivative is equal to, again, same thing, outside inside. So first you are differentiating the outside function, which is f, keeping the inside g of x intact. Because do not forget that this f composition g of x is after all f of g of x. So f is the outside function. We are differentiating the outer room without changing the inner room, and then multiply that with the derivative of the inner room, that is g of x. That means g prime x. But because f is given in terms of the variable u, so it makes sense that we write u here, otherwise it will be a little confusing. Now what do you get when you differentiate f with respect to u? Differentiating 1 with respect to u, you get 0, of course. What does 1 divided by u give you? You have already differentiated this function, that is the reciprocal of the variable, many times before, and this is minus 1 divided by u square, but already there is a minus sign. So this becomes 1 divided by u square times g prime of x, which is this, with a minus sign. I should have put one more set of brackets here, otherwise it looks very confusing. But how is this g prime of x minus 1 divided by x minus 1 square? Actually, in calculating this derivative itself, also there is an application of the chain rule. Let's see how. So what is your g of x? 1 divided by x minus 1, which is just x minus 1 to the power minus 1. So here also you are actually looking at the composition of two functions. One of them is your reciprocal function, and the other one, the inner room here, is x minus 1. The outer room is the reciprocal room. So in differentiating this, you have to again apply the chain rule. So if you differentiate your ordinary reciprocal function, or here you are viewing it as your inner room to the power minus 1. So you can apply the power rule with negative exponent. Minus 1 comes down, and then you subtract 1 from the exponent, you get minus 2. But then you have to multiply that with the derivative of the inner room. Now if you differentiate x, you get 1. Differentiating 1, you get 0. So that means the inner room actually does not contribute anything ultimately. And you are just left with this, which you can write as a fraction, minus 1 divided by x minus 1 square. So that is how this is coming. And now of course we will write what u is, that is this thing, and then only we can evaluate the derivative at x equal to minus 1. Because u itself is 1 divided by x minus 1, so 1 divided by u would be x minus 1, but we have square of that. Square of that means you can view this as 1 divided by u whole square as well. So that is why in its place you have x minus 1 square, and with that you have this. So after cancelling these two things, you are left with minus 1. So it is constantly minus 1. So at the point x equal to minus 1 also it will be minus 1. Let's do another one of this type, number 58. Here the function f of u is the square of u minus 1 divided by u plus 1. And where u itself is this function g of x of the variable x, and that is 1 divided by x square minus 1. And here also we have to find the derivative of the composition at the point x equal to minus 1. So the beginning of course is same. We just calculate the derivative at any point x, which by the chain rule is this, f prime at g of x times g prime at x, and then you write u in place of g of x because that is what it is, and then you actually do the differentiation. In differentiating f itself, you have to again apply the chain rule, because here there is an outer room which is the square room, and this is the inner room which itself is a fraction. So if you differentiate the outer room by the power rule, usual power rule, 2 comes down and then you subtract 1 from the exponent. So that's how you get 2 times the inner room, the first power of the inner room, because you are subtracting 1 from the exponent, 2 becomes 1. So you have that 1 here. And then you multiply that by the derivative of the inner room. Because the inner room is a quotient of 2 functions, you have to apply the quotient rule, in which you of course do whatever you need to do. That means you take the square of the denominator here and write that here. Then what is the numerator? In the numerator, first you write the denominator as it is, u plus 1, so you have written u plus 1 here, and then multiply that with the derivative of the numerator. If you differentiate u minus 1 with respect to u, you get 1, because differentiating u, you get 1, and differentiating 1, you get 0. And then minus, you then keep the numerator intact, which is u minus 1, and then multiply it with the derivative of the denominator, which is 1 again, because differentiating u plus 1 with respect to u also gives you 1. And then do not forget that you also have this g prime of x. What is g of x? This is g of x. If you differentiate 1 with respect to x, you are getting 0. But what will you get when you differentiate 1 divided by x square? For this you have to apply the power rule again with negative exponent, because this is x to the power minus 2. So that minus 2 comes down and becomes minus 2 here, and then you subtract 1 from the exponent, which now is minus 2, x to the power minus 2. So it will become minus 3, and when you write that back as a fraction, you get minus 2 divided by x cube. And then we have to now simplify this, and then we do the evaluation at x equal to minus 1. Because the expression is quite complicated, so we move carefully. We first write what we can immediately see. We have a 2 there and we have u minus 1, so we wrote u minus 1. And you also see that you can write u plus 1 whole cube here. Now what about this part? It is just u plus 1 minus of u minus 1, or u plus 1 minus u plus 1. That means it is 2. So that's why we wrote 2 here, and along with that of course we have minus 2 divided by x cube. And now only we see what all these things give us together. Already there is a minus sign. 2 times 2 times 2 is 8, and with that u minus 1 divided by x cube and u plus 1 whole cube. Now let us separately see what u becomes when x is minus 1, because u is a function of x. So at x equal to minus 1, u is this g of minus 1. G of x is 1 divided by x square minus 1. 1 divided by minus 1 whole square minus 1. So this becomes 0. When x is minus 1, u is 0. So now it's a bit easier to calculate. So f composition g prime at minus 1 is this. U is 0, u is 0 here, and you have put x equal to minus 1. So the numerator is becoming minus 1, and the denominator, this part contributes 1, so that thing vanishes, and again you are having minus 1. So after cancelling this minus 1 and minus 1, you are left with minus 8. So that is the answer. Next, let us see this number 66, which has 4 parts. This is the first one, part A, and it's geometric in nature. Find equations for tangents to these two curves, y equal to sine 2x and y equal to minus sine x divided by 2 at the origin. Is there anything special about how these two tangents are related? We have to give reasons for our answer. So we first find the tangent to the first curve y equal to sine 2x at the origin. And for that we need to know the slope of the tangent at the origin. So let us first calculate the slope at any point by, of course, finding the derivative. Derivative is slope. Now to differentiate this, you are going to again need the chain rule, because it's a composite of two functions, the outer sine function and the inner function 2x. So if you apply the chain rule, what will you get? You are going to differentiate the outer function first, that will give you cos, keeping the inner room intact 2x, and then you multiply that with the derivative of the inner room. Differentiating 2x, you get 2. So that 2 I have written here. So that is the slope of the tangent to this curve at any point x. But we want the slope at the origin, and for that we need to put x equal to 0 here. And when you do that, you get cos 0. Cos 0 is 1. So the slope becomes 2. So this is the equation of the tangent to this curve at the origin. Why though? That is because how do equations of lines look when they pass through the origin? Y equal to mx, where m is the slope. That is why here slope is 2, so y equal to 2x. Now we do the similar thing for the other curve, y equal to minus sine x divided by 2. The slope of the tangent to this curve at any point x is this m2. Again you differentiate this using the chain rule. Differentiating the outer sine function gives you cos x divided by 2, and then you differentiate the inner room, which gives you 1 divided by 2. Because there was already a minus sign, so you find a minus here. That is the slope at any point x, but we want the slope at the origin. So for that we put x equal to 0 here, and that way we get the m2 value minus 1 divided by 2. And so the tangent here is y equal to minus x divided by 2. Now next we have to say how these tangents are related to each other. To see how the tangents are related, you look at their slopes m1 and m2. m1 is 2 and m2 is minus 1 divided by 2. So if you multiply the two slopes, you are getting minus 1. But you already know that when that happens, the two lines are perpendicular to each other. That is why the tangents are perpendicular to each other. Part B is similar but general in nature. Here the curves are y equal to sine of mx, and the other one is y equal to minus sine of x divided by m, where m is a non-zero constant, non-zero real number, which does not change with x. Now, can anything be said about the tangents to these curves at the origin? Well, I forgot to write at the origin, but at the origin. Give reasons for your answer. Exactly same thing. Here also the tangents will be perpendicular to each other, and I urge you to similarly go through the steps and find the tangents to these curves at the origin. Next, part C. For a given real number m, what are the largest values of the slopes of these curves? Y equal to sine mx and y equal to minus sine x divided by m. And that's it. Here not at the origin or anything, okay, at any point. That is why the slope will vary. We have to find the point where the slopes are the largest to these curves, and we have to give reasons for our answer, of course. So instead of an elaborate solution, I am giving you hint. Actually this has everything you need to know to write a solution. This is hint in the sense that I did not write any sentence or anything. So if we just simply calculate the slope of this curve, slope of the curve or slope of the tangent at some points same meaning. You just have to differentiate this. So you differentiate this using the chain rule. Differentiating sine first, you get cos of the inner room mx, and then you differentiate the inner room, which gives you m. So the slope m1 is m cos mx, and then you look at its absolute value. So that will be equal to the absolute value of m times the absolute value of cosine of mx. You know that cosine value is less than or equal to 1, absolute value is less than or equal to 1. So the largest that this slope can be is this. Okay, that is the largest value, the absolute value of m. And when will that happen? That will happen precisely at those points x for which cos mx is equal to 1 and x equal to 0 is one such point. So at the origin, the slope of the graph of this is the curve that will be maximum numerically. M may be negative, but numerically that will be maximum. Elsewhere it will be less than that. What about the second curve? You similarly calculate the slope by differentiating the given function. So that way you get minus 1 divided by m times cosine of x divided by m. And then here also you calculate the absolute value, and here also you get that the maximum value is this. Absolute value of minus 1 divided by m, or 1 divided by the absolute value of m. So that is the maximum numerical value that the slope can have on this curve. So here also you can see that at the origin in particular, that maximum value is reached. Depends on m how the curve actually will look, but you can understand that it will just be a sine curve, both of them. M will determine how steep, how the curve will move, whether it will be something like this or something like this. Whatever the case is, on the first curve, this is the maximum slope numerically, and on the second curve, this is the maximum slope numerically. And finally, we have part D, in which we consider the ordinary sine function. We know that it completes one period on this interval 0, 2 pi. Whereas in that same interval, the function y equal to sine 2x completes 2 periods. But the function y equal to sine x divided by 2 completes only 1/2 of a period, and so on. Now, is there any relation between the number of periods that this function y equal to sine mx completes in that interval and the slope of this curve at the origin? Yes, and the answer is that they are the same. Give reasons for your answer. That is left to you. So what the answer is? The answer is that these two things are the same. Now you figure out how they are the same.